Next speaker, Mr. Raghav Segal from Yale University. Raghav, are you ready?
I am.
All right, go ahead.
I do need access to the. I don't seem. Oh, I seem to have access now. Well, thank you everyone for being here today, and I will start my presentation. I'm a PhD student at Yale University, and just some quick conflicts of interest. Some of the work that I'm going to talk about is also been licensed out and is part of a patent. I'm also a scientific advisor at Longevity Tech Fund, and I'm a scientific advisor. I have been a scientific advisor at Cameron Biopharma, and I've consulted them for clinical biomarker strategy. So just wanted to give a heads up on that. So some key focus points of my talk are going to be today about what is a clock in context of aging biomarkers, the types of epigenetic clocks that typically exist out there, and which of these aging clocks or epigenetic aging clocks specifically may be best for assessing longitudinal changes in social and behavioral studies. And I'll talk about this through two examples, one a behavioral intervention and a psychosocial longitudinal study. So to start with, what is a clock, specifically in context of aging biomarkers? And so a clock is something that essentially will help you measure time. It'll tell you something about time. So, and in that context, biological clocks will tell you something about the time of your body. They might tell you the time that has passed, so the time since your birth or your chronological age. They might tell you the rate of time passing or the pace of aging, or they might tell you the time left or your time to death or mortality. And how do biological clocks really do this? They do this by first either selecting a data type. This could be DNA methylation, proteomic, clinical biomarkers, phenomic data like MRI data. They then typically look at a global aging phenotype like the ones I just talked about. They could be time to death, pace of aging, chronological age, and then they typically build a machine learning model which takes into account DNA methylation or proteomic data, and then have an output like time to death at the end. And that is effectively what a biological clock or an omic clock really tries to do. And so an epigenetic clock is essentially a machine learning model that uses DNA methylation to predict an aging phenotype like time to death at the most simplest level. And so that brings me into all the epigenetic clocks that have been developed over this period of time. So the first kind of epigenetic clock was a very simple 3-CPG predictor that came out in 2011, and that kind of led to the boom of epigenetic clocks, with the first generation of clocks measuring what we call as time past or chronological age, which we call the generation 1 clocks, which were sort of the Hannum and Horvath 1 clock. The second generation of clocks like phenoage and grimage were measuring time left or sort of mortality. And then more recently, the Gen X clocks, which Dan Belsky would be talking about later today, or the rate of time passing, measure sort of pace of aging. And each of these clocks have been really amazing at what they do and have provided a lot of insight into the workings of aging. But before I sort of talk more about which of these clocks are really valuable and how we can use them, I want to talk about some other key points about epigenetic clocks. And some key in concepts here, one of the most key important concepts here is age deviation, which was formerly known as age acceleration, but now sort of the field is moving towards calling it age deviation. So age deviation is nothing but the residual of biological age after adjusting for chronological age. So essentially, you draw a very simple linear model of biological age as calculated by one of these epigenetic clocks or maybe any other type of omic clock with chronological age, and you find the difference between sort of your biological age as compared to this sort of this straight line drawn by this linear model. And this residual or this error that you're seeing here has been shown to be associated with a wide variety of aging phenotypes, such as mortality, frailty, risk of a wide variety of diseases like CVD, so on and so forth. Rather, we have seen that not only is this associated with the causes of diseases of aging, such as mortality, CVD, outcomes such as mortality, CVD, so on and so forth, but also causes of aging, such as low SES, low education, BMI, so on and so forth. And another key important concept here is the idea of more reliable epigenetic clocks. So typically, epigenetic clocks that were built in the first and second generation were really noisy. So take an example here for PhenoAge, which was a second generation epigenetic clock, which you can trace on this particular plot here. On the x-axis, you have on the x-axis is essentially time. On the y-axis is the methylation age for individuals, and each line here is one particular individual changing over a period of time. And so you can think about this one particular individual in pink, which is going here, and what you can really see is that from 0, which is their baseline age, they go almost till minus 45 in their epigenetic age over a period of just about 7 years, which doesn't really make sense that they will change so dramatically over such a short period of time. And this is not necessarily a biological change in their age, but potentially just noise that is being captured due to sort of some technical issues in the methylation data processing. And this was something that was resolved by capturing a method called PCA or PC clocks. And because of the limited time, I will not go into the methodology of this, but this was essentially be able to fix by using PCA and get a more sort of less noisy version of these clocks, which you can see now on the right-hand side. And you can see that these clocks have a lot less variation and are tracking much better with age and have a lot less error over a period of time. So these clocks are essentially a lot better now and will have a lot less error and a lot more reliable. And moving forward, we'll talk a little more about how these PC clocks are potentially better as well. But that brings us to the question that there are so many clocks. There's the Gen 1 clocks, the Gen 2 clocks, the Gen X clocks, and now the PC clocks. So which of these clocks should we really use for the purpose of studying social and behavioral interventions? And that brings us to our next section, which of these aging clocks may be best for assessing longitudinal changes in social and behavioral studies. And for this, I would like to first go into one case study where I would talk about the effects of low-fat diet on epigenetic age, which is a behavioral intervention study that we have looked at in my research. So this is part of in this study, we are looking at the central trial, and the central trial is quite large. We're just looking at one part of the central trial, which is the low-fat arm of the central trial. It has a Mediterranean diet arm. It also has like an exercise arm. We're just focusing on the low-fat diet arm, at least for this particular presentation, but we can talk more about the other parts as well if you'd like. And in this particular part, we have 60 individuals aged 28 to 71 who were put on a low-fat diet for 18 months, and we have paired DNA methylation samples at the time point 0 at the start of the diet and at time point 18 at the end of the dieting periods for all of these 60 individuals. And so I want to take you through exactly how we did this analysis so that you guys can replicate this analysis as well, potentially for your studies. So the first step is, of course, after we get the DNA methylation beta score values, which is the standard output you will get after any DNA methylation data processing, we use that to calculate the epigenetic clocks in R using the methyl cipher package. You can read more about the methyl cipher package in this publication, which I have attached below. after which we calculate the age deviation. For those of you who use R, you would understand this sort of very simple line of code where I'm calculating the residual of the linear model of epigenetic clock after regressing out age, as I previously explained. And then the final step is I perform a paired t-test on the residualized epigenetic age scores as to get essentially whether there is a significant change or not between time point 18 and time point 0. Or between 18 months and 0 months for these different clocks. So as you can see, it's a very simple analysis that will, a 3-step analysis that will give us these results, and hopefully you can replicate this analysis for your own studies. So let's actually go into what we are seeing for these studies. To start with, first let's look at one of the generation 1 clocks, which is PC Horvath, where we see, so just to quickly understand this graph, we have baseline, which is 0 months and 18 months here, and on x-axis, on the y-axis, we have age deviation, which is essentially the residual of biological age from the chronological age. Each point is one individual connected from their baseline age residual value to their 18-month value. And what we are seeing is a general trend that they are typically decreasing in age or in their sort of residual age deviation values, but that change doesn't seem to be significant. It is not significant. We then look at, we then look at some of the generation 2 clocks as well. And it seems like the generation 2 clocks also do not show significant change, neither for PC pheno age nor for PC crim age. The question then is that, is this a problem with the clocks, or is this a problem with the interventions themselves? So we do know that in this clinical trial that individuals do show a loss of weight, significant amount of loss of weight actually, and we do know that weight loss does improve markers of inflammation or decrease in markers of inflammation and may potentially decrease the rate of aging. Then why are these epigenetic clocks potentially not capturing it? And that brings us to the question, what are these epigenetic clocks really measuring? So epigenetic clocks like these are typically measuring what we call as whole body aging. They're typically measuring sort of taking blood from whole blood DNA methylation and making sort of proxies of whole body aging. And so some interventions may affect whole body aging, such as an intervention that might affect potentially all of the like cellular regeneration or cellular reprogramming that might affect all of the whole body. But there might be other interventions that might be more specific and thus might not be captured by the whole
2 minutes remaining.
And will be targeted by very specific and there might be very specific parts of the body that would be targeted and thus may not be captured by these whole body epigenetic clocks, and thus there would be not really significant changes in these whole body epigenetic clocks. So what we might really need are sort of very specific epigenetic clocks that are capturing changes in these very specific different parts of the body. And for this very purpose, I have been working on organ or system-specific aging from whole blood DNA methylation as part of my research, where from just whole blood DNA methylation, we can capture organ-specific aging. The way I'm able to do this is, and what we have been able to show is essentially these organ-specific aging from DNA methylation is highly specific, as in the brain score it has been shown to be associated with cognitive function. The musculoskeletal score has been shown to be associated with arthritis. The heart score has been shown to be associated with coronary heart disease, so on and so forth. And so what we see is that, for example, in the previous central trial intervention, low-fat diet intervention, the low-fat diet reduces aging in the musculoskeletal system quite significantly. We see about a 2.4-year reduction. And this is not the only system we see a reduction in. We actually see that there is 6 different organ scores where we see significant decrease. We see 1.7 years of reduction in the inflammation score, 1.85 years of reduction in the metabolic score, 1.2 years of reduction in the kidney score, 0.95 years of reduction in the heart score, and 0.55 years of reduction in the blood score. Overall, we see a very nice picture of how the low-fat diet really affects the different organ-specific scores or organ-specific methylation scores, something we could not previously have seen from the whole body scores. And just to remind you, all of this is being captured from a single whole blood DNA methylation blood draw. The same amount of DNA methylation blood draw that was required to capture Prim age or pheno age or Dunedin pace or any of the other clocks. And so with this, I'd like to move into one of my second studies, the effects of military deployment-related PTSD on epigenetic age, a psychological longitudinal study. And so in the Prismo study, we had 108 individuals with 3 DNA methylation time points where we did a paired t-test analysis, which was done of age-resolution, and we did t-test analysis of age-resolution epigenetic clock values for T1 and T0 and T6 and T0. For these individuals. So we had pre-deployment data from pre-deployment, and these individuals were taken to deployment in Afghanistan, and then we collected data at 1 month post-deployment and then 6 months post-deployment. What we see was in whole body clocks like Grim age, there was no significant change at 1 month post-deployment compared to pre-deployment or 6 months post-deployment compared to pre-deployment. For PC pheno age, we did see a significant change at 6 months post-deployment. And so that was actually a 1.2 years of age acceleration at 6 months post-deployment. But it gets really interesting when you look at organ-specific clocks, specifically for lung aging, where we see about 2 years of age acceleration at the 1 month mark, and 2.6 years of age acceleration at the 6 month mark. And this is really interesting because this, we believe, is not really related to PTSD, but it's probably related to the fact that a lot of military personnel in Afghanistan experience sort of smoking-related effects and chemical exposures. We also have increased this thing in the musculoskeletal aging of 2.1 years, liver aging of 1.9 years increase, heart aging of 1.3 years, and inflammation aging of 1.35 years. And so again,
if you could begin to wrap up some final thoughts, that'd be great. Thank you.
And with that, and so we see a really nice picture of exactly what's changing in every specific organ. And with that, I'd like to sort of just point out some key takeaways here that there are very specific, that the ML models that tell Omic clocks can tell us about the time spent, time left, or rate of time of a person's body using biological data. There are different types of epigenetic clocks and there have had multiple evolutions. Gen X and PC clocks are the latest version of whole body clocks. And then breaking down clocks into biological systems can give a lot more insights about sort of longitudinal and social behavioral changes. Thank you.
Thank you, Raghav. It's wonderful.